Good afternoon, student. In a previous lecture, we studied about the light and the term related with the light and also the interference of light. When we talk about the light, there is the some terms are reflection, refraction and the transmission. When we consider the light rays is incident on the surface, that is made between the medium 1 and the medium 2, then this light get partially bent in a same medium and partially bent in another medium. Then the rays bent in a same medium, that rays is called as a reflected rays or called a reflection. And the rays get bent in another medium, means from medium 1 to medium 2, then this ray is called as a refracted rays or called a refraction. After incident here, these rays again get reflected and the reflected. These refracted rays are or directly come out from the medium, that rays is called as a transmitted rays or the transmission. Again, this reflection and the refraction is a partial reflection and partially. That to find out that reflected and the refracted rays, we use the Fresnel equation. This is rho equal to mu1 minus mu2 upon mu1 plus mu2, where mu1 is the refractive index of medium 1 and the mu2 is the refractive index of the medium 2. If suppose mu1 is greater than the mu2, that implies rho is positive. That implies the oscillation between the incident rays and the reflected rays are in a same phase. In second condition, if mu1 is less than the mu2, then the rho become negative. Here, if mu1 is less than mu2, then this term become negative, therefore rho become negative. It means that the oscillation of incident rays and the reflected rays are the out of phase, means there is the phase of difference. That implies the two waves are the out of phase. From this condition, we concluded the two conclusion. The first is that if the rays, suppose this is the rare medium and this is the denser medium, if the rays is comes from rare to denser medium, means that from rare to rare and incident here, and from denser medium to rare medium, then there is the part difference. Then these two rays are out of phase and occurs the part difference pi. Then there is a phase difference and that phase difference is of the pi. It means 180 degree out of phase. And if the rays is coming out from denser to rare medium, means here from denser medium to rare, this ray travel in a denser medium and come out in a rare medium, then there is the no phase change. There is the phase change is a 0. This is the phase change due to the reflected rays and the refracted rays. Now next is the thin film. Thin film is the medium having the thickness 10 micrometer. For example, the soap bubble, air film, which is composed between the sheet or the glass film or the mica sheet, that is called as the thin film. We study the interference in a thin film due to the reflection. For that, we consider the thin film. This is the thin film having the thickness t and the refractive index mu. When the light rays is incident on the surface of the thin film by making an angle I with the normal, this is the normal, by making an angle I, then it get partially reflected along the BC and partially refracted along the BF. Again incident here at point F, it again get reflected internally along the FD and after that it come out along the DE. This shows that the HC and the DE travel the equal path. That CH and the DE travel the equal path, but if we observe the geometrical path difference between the BC and the DE, the DE travel this extra path BF and the FD. Therefore, the geometrical path difference between the BC and the DE is BF, this BF plus FD minus BH. This is the extra path is covered of these two lines. Therefore, the geometrical path difference is BF plus FD for this rays BD and minus BH for the CH. This is the equation. Then according to the definition of the optical path, it is written as mu means refractive index into the geometrical path difference. Here the that rays in a thin film travel into the thin film and that rays travel in a air film. Therefore, we use the refractive index of the thin film and the refractive index of the air. This equation becomes that mu d into Bf plus Fd minus mu a into Bh. Mu a is the refractive index of the air and it is mu a equal to 1. The value of mu a is a 1. Then this equation becomes mu d equal to Bf plus Fd minus Bh. This is the equation number 1. Now, in triangle BFD, we draw the one normal FG by making an angle R. This angle is called as a refracted angle. In triangle BFD, we consider that angle BFG and the angle GFD. BFG and the angle GFD, which is equal to the angle of R, means refracted angle. This is the R, and that BF and the FD are the equal. Then in angle BFG, the cos of R means adjacent upon hypotenuse. This cos of R in angle BFG, the adjacent is the FG and the hypotenuse is the BF. Similarly, in triangle GFD, the cos of R becomes FG upon FD. FG upon FD. The value of FG is a small t, means it's a thickness of the film. After substituting or after rearranging this equation, these two equation, we get the BF equal to FG upon cos of R and FD equal to FG upon sin of R. And substituting the value of FG is the thickness of the film, which is nothing but the small t. We substitute here, we get the BF equal to T cos of R and FD equal to T sin of R, and therefore the BF plus FD becomes 2T cos of R. This is the equation 2. Now here that BD, in a BD, that BG equal to GD, and therefore this BD, complete BD equal to two types of BG. Here BG equal to GD and therefore that BD equal to 2 times of the BG. This is the equation number 3. In angle BFG, we get the sin of R equal to BG upon FG and the cos of R equal to FG upon BF. In BFG, sin of R equal to BG adjacent upon, sin R mean opposite upon hypotenuse. The BG upon BF and the cos of R is a FG upon BF. Here we use these two terms. Now then the definition of the tan R is a sin R upon cos R. We get this ratio. We get the tan R equal to BG upon FG and that same term BF cancel. Then from this equation we get B G equal to Fg tan R. Okay. Then Bg, again Fg is the thickness of film which is equal to small t. So Bg equal to T tan of R. From then T tan of R. Now in triangle BHD, we draw the hypotenuse, normal on the axis, we get the triangle BHD. From this triangle we get the sine of I equal to BH upon BD. Again sine I means opposite upon hypotenuse. So here we get opposite BH and the hypotenuse BD. Here we get BH upon BD. From this equation we get BH equal to BD sine I. This is the BD sine I. And we have the value of BD here. BD. Then substitute this value of BD in this equation. We get the BH equal to 2T tan R sine of I. Now this is the equation 5. Now we know that the Snell's law. This Snell's law is the sine of I upon sine of R equal to mu. From this equation we get the sine of I equal to mu sine R. Then substitute this value in equation 5. Then we get BH equal to 2T sine of R. This tan R means sine of R upon cos of R, and sine R means this term mu sine R. Then solving this terms we get BH equal to mu 2T sine square R upon cos R. Then this equation. Then substitute all these terms, this BH and the BF plus FD, this equation in a equation 1. All terms in the equation 1 we get del equal to mu 2t cos of R minus 2 mu t sin square R upon cos of R. Rearranging this equation we get 2 mu t. Here 2 mu t is a common term upon cos of R. We get here 1, this all terms 1, and here we get the sin square. So 1 minus sin square, since 1 minus sin square R equal to cos square R. We substitute this value here. We get cos square, cos R cancel. We get the cos R. Therefore, final term is a delta equal to 2 mu t cos of R. Now, we know that due to the reflected rays, there is the path difference between the incident rays and the reflected is a pi or a 180 degree or lambda by 2 in between the incident rays and the reflected rays. Therefore, this term become 2 mu t cos of R minus lambda by 2. This equation number 7. Now the condition for the maxima. We know that reflected rays travel in a medium and get intersect with each other from the interference. But according to the optical path definition, the condition for maxima is delta equal to m lambda. When we substitute this value in equation 7, then we get m lambda equal to 2 mu t cos of R minus lambda by 2. Rearranging this equation means take this term here, we get m lambda plus lambda by 2. So after solving this, we get 2 mu t cos of R equal to m plus half lambda. This is the condition for the maxima. Similarly, the condition for the minima. Then for the minima, the optical path is equal to m plus half lambda. We studied in a previous lecture. Then substitute this value in a equation 7 and we get the equation m plus half lambda means this term equal to 2 mu t cos of R minus lambda by 2. Again take this term here, we get 2 mu t cos of r, m plus half lambda plus lambda by 2. After solving this, we get 2 mu t cos of r equal to m plus 1 lambda. Again we get this m plus 1, where m is the integer multiple, where m equal to 0, 1, 2, 3, 4 and so on. Therefore that m dash is become the integers, which is m 1, 2, 3, 4 and so on. Then this is the condition for the minima for the thin film due to the reflected rays. Thank you.